Hello, welcome to Group 1's presentation, Modern Data Architecture, Big Data, Hadoop. Group 1 is comprised of Adam Beck, Karen Beyer, myself, Zach Bishop, and Caitlin Jones. For people overseeing a warehouse or data mart, how would big data and the Hadoop platform fit in with their overall data and information management strategy? What even is big data? Big data is various forms of smaller data pulled together to tell a story or multiple stories that can then be used to help drive business decisions. Companies are recognizing the potential goldmine this information deluge could offer and want in. In turn, this desire is creating a new way of looking at a company's roadmap, strategy, innovation, and potential. This leads to the question, what has become the modern data architecture? The answer to that question can be found in a quote from CITO Research via Attunity. Quote, "A modern data architecture includes multiple repositories. It incorporates Hadoop, traditional enterprise data warehouses, and other data stores. These repositories may reside in many different locations. It includes cloud data sources and can incorporate public or open data source as well as commercial data sources. Data from mobile devices, sensors, and the Internet of Things are also included in the notion of modern data architecture. The data supply chain connects and feeds all of these sources into the modern data architecture." End quote. As you can see from the diagram, modern data architecture is not simply linear, but very much circular, with many areas and entities working and being affected by the use of big data. The cost of Hadoop data management system, including hardware, software, and other expenses, comes to about $1,000 a terabyte, about 1/5 to 1/20th the cost of other data management technologies such as network storage. If you look at network storage, it's not unreasonable to think of a number on the order of about $5,000 per terabyte. Sometimes it goes much higher than that. If you look at databases, data marts, data warehouses, and the hardware that supports them, it's not uncommon to talk about numbers more like $10,000 or $15,000 a terabyte. Legacy data management technologies often store multiple copies of the same data on different systems. The total cost might be more like $30,000 to $40,000 per terabyte. It's easy to see why for so long it wasn't financially feasible for a company to record and store any and all data it could corral. Hadoop is able to store and distribute enormous data sets across hundreds of inexpensive servers that all operate in parallel. This enables business to run applications on thousands of nodes involving thousands of terabytes of data. Hadoop has proven effective in a variety of industries. In manufacturing, for instance, Hadoop is used to assess product quality. In telecommunications, it's used for content mediation. It's also popular among government agencies for a variety of applications including security, search, geospatial data, and location-based push of data. It can process a diverse set of data from structural to unstructured and semi-structured and allows for storage of data up to 1 petabyte. This Hadoop thing sounds great, but you're probably wondering how it works. Data in a Hadoop cluster is broken down into smaller pieces, called blocks, and distributed to different nodes throughout the cluster, allowing for parallel processing. Then, copies are made of each piece of data multiple times and distributed the copies to individual nodes, placing at least one copy of on a different server rack than the others. By doing this, the data on nodes that crash can be found elsewhere within another cluster. This allows processing to continue while failure is resolved. An additional benefit of Hadoop is it allows for massive scalability across hundreds of thousands of servers in a Hadoop cluster. The way that works is there are two separate tasks. The first is the map job, which takes a set of data and converts it into another set of data, where individual elements are broken down into tuples, key pairs. The second job is the reduce job, which takes the output from a map as input and combines those data tuples into a smaller set of tuples. An analogy would be, there is a census taker in each city that is tasked with counting the number of people in that city and returning to headquarters. There, the results from each city would be reduced to a single count, the sum of all the cities, to determine the overall population. This mapping of people to cities in parallel and then combining the results, reducing, is much more efficient than sending a single person to count each city. There are also some disadvantages to using Hadoop. It lacks referential data integrity checks, validity of data in dates and account balances that a relational database management system puts forth as normal applications to database design. Missing from Hadoop are robust indexing strategies in database operators, advanced memory management, concurrency, and dynamic workload management. There are security concerns. The security model is disabled by default because it is so complex and requires a subject matter expert to come in and enable it. It's written almost entirely in Java, which has been heavily exploited by cybercriminals, making it incredibly vulnerable. In addition, it's not a great fit for small data or executing ad hoc queries. It's also important to remember that there are other services and applications, and it may be necessary to combine them with Hadoop to truly get the most information out of your data. The best way to be successful is the enterprise data warehouse working side by side with Hadoop. Enterprise data warehouses are still very much needed in that they offer value that Hadoop doesn't, and vice versa. Data warehouses use structured, relational data right for analysis. Hadoop is best at processing unstructured/semi-structured or log data. Real-time analytics is best served via the traditional data warehouses. A traditional database is still a necessity for managing day-to-day business operations, and the majority of businesses simply don't have the resources or expertise needed to run a Hadoop cluster for every data query. An investment in Hadoop requires an investment in a cluster management team in addition to infrastructure. There's a bright future ahead for big data. There's quantum computing, which may not be commonplace in 2016, but significant strides are being made in coding required to make this an everyday reality. Artificial intelligence and machine learning, the Internet of Things, quote, will allow devices to automatically collect, store, and analyze data, of which there will be a huge increase in the next 12 months. Though the use of both AI and machine learning, it becomes possible for these huge amounts of information to be processed, stored, and mined without needing human interactions to do so, end quote. Big data is gaining ground in terms of overall comprehension of what it is and isn't. The term big data has become more understood and commonplace. Data science isn't database management. Thank you for listening, and have a wonderful day.